Chapter 7.1 is about the area between curves. Good first question would be, why should we care? There's something called hysteresis that involves energy loss in all kinds of systems, electronic engineering stuff. There's hysteresis in biology, economics, all kinds of interesting stuff. Let's go see that. So here's the Wikipedia page for hysteresis. Here's a curve that shows as you apply more magnetic field to something, on the y-axis it gets more magnetized. When you relax the magnetic field, it doesn't lose all the magnetization you gave it, and then when you reverse the magnetic field, you end up magnetized the other way. And if you've got alternating current, you keep going around and around this loop, and the area between these curves is how much energy you lose each time you go around. So that's kind of why your power supply warms up. It's part of the reason your power supply warms up. It's part of electrical losses in the electrical grid, all kinds of important stuff. It's also related to how hard drives store information. It's so important there are statistical packages for estimating hysteresis curves and everything. We'll see about that. Another application of the area between curves is analyzing how many people have arrived to a system so far, how many people have left. Everyone who has arrived but not left is waiting in line, and you want to figure out the average waiting in line, so you end up with the area between curves there. So those are some nice applications, but it's in all the calc textbooks because it's a chance to practice something simple in kind of 1 or 2 dimension before we move on to thinking about volumes of rotation, getting all confused in 3 dimensions. So the idea is to start simple. Let's start with a fairly simple problem. How about the area between x squared and x cubed on the interval 0 to 1. So the first thing I would do is draw it. X squared looks something like that. X cubed looks something like that. Here's one, x squared, x cubed. So what's the area between those? Well, one way of thinking about it, since we're used to thinking about areas kind of almost geometrically, you could say, well, I'm going to think about the area between x squared and the x-axis, so this whole area. But that includes some area that I didn't want, so I'm going to subtract the area that I didn't want under x cubed. And that would be fairly simple, right? The integral 0 to 1 x squared dx minus the integral 0 to 1 x cubed dx. So nothing wrong with that way of thinking, but here's a chance to practice one of the big ideas of calculus, and that is if you have a hard problem, let's break it into smaller, simpler parts and then add them all back together. So that's one of the big ideas of calculus. The big idea. Break a hard problem into tiny pieces, tiny easier pieces. Another name for that is discretizing, to turn something from continuous into discrete. Compute each and then add it all back together. And how do we add stuff back together? We write an integral, or integrate. So how can I take this problem and break it into smaller, easy pieces? We'll look at those 2 curves again. And we'll say, when we first learned about integrals, we broke things into boxes, right? And Riemann sums and all that. So here we could break this into a box like that and another box like that. So each box, I'm being kind of sloppy in how I draw it, but the box kind of starts down here at the lower curve and goes to the upper curve, right? So what's the area of this box? Well, the area of any box is what? Height times width. what's the height? Well, it's the difference between the upper curve and lower curve. So that would be x squared minus x cubed times the width. Well, how skinny should we say that box is? Well, when we were doing integrals, we started with delta x usually, and then we let delta x go to 0, and then we said we'll call that dx. So we'll just call it dx here. So to add up those boxes, we'll do the integral, and here we were going from 0 to 1, so we'll just go from 0 to 1 there, of the heights of the boxes, so x squared minus x cubed times dx. And that's breaking the problem into smaller, easy pieces, little rectangles, and then putting them all back together. Does it make sense that this formula and this formula should give the same answer? Because you can just break the integral of the difference into the difference of the integrals. Yeah, so it's not a big intellectual advance here, but it's a stepping stone on our way to other things. So let's go try another problem in the next video.